Hi, this is Brian with Degrees of Freedom. I wanted to take some time to talk about some of the technical development efforts that went into our Kinetasphere watch box. So this is a spherical kaleidocycle that carries a moving platform that securely supports a watch on the inside. That watch lives on a little mechanical pillow. So this is mechanically a relative of our kinetic ring box. So the movement is very similar, but the payload is a lot heavier. And what I'd like to talk about is how that was a uniquely challenging process of going from a little payload to a big payload in a way that was safe and secure for the customer. So a mobius kaleidocycle, for some background, is a single degree freedom mechanism, a closed loop of 6 links. The thing with single degree freedom mechanisms is they don't usually like to be spanned or short-circuited. That'll usually end up binding them. So for the engagement ring box, I honestly did kind of a lazy thing, which is to avoid over-constraining it, I basically gave the platform, I needed some way to suspend and support a ring inside this box that I wanted to use to propose in 2018. So what I did is I gave the platform all of the degrees of freedom by making it out of a very compliant material. So this is the pillow taken out, and it is floppy, but very, very deliberately so. And what's important is that this is dramatically floppier than this. This is all machined aluminum. So by this being orders of magnitude stiffer than this little guy, this will run the show, this will mechanically stay out of place, but it's still sufficiently structural to be able to hold a ring like this. So when it came time to do a bigger payload, that was kind of the natural next question, is like, what other things could I do with this same construction? Could I hold other things? Another piece of jewelry that people really like that's precious is a watch. And but it was immediately apparent it wasn't going to be as simple as just plopping a watch in here, because it would be very floppy when it was that heavy. So I needed some way to very securely mount and carry a heavy payload inside the mobius kaleidocycle, which meant that I needed to have basically stiffness parity between the carrier support and the external enclosure. So I needed to truly have a single degree freedom mechanism that included this, which is kind of a mess. So what I'll do is kind of talk through how I made the enclosure, how I got the carrier in, and then how I finished the enclosure to create kind of the proper tactile experience for the customer. So the first thing I wanted to do was see, can I turn this into a sphere? And the way I kind of thought about it was, if I just inflate these outer surfaces, can I allow it to articulate if I keep all the same break lines and break planes? And it did. So you can see these back panels, I really did just bond a little spherical panel onto these. These outer ones I did thin them out a little bit. And you can kind of see the square, the cubic shape to it, maybe. And what the break lines, it's just projecting planes out of the middle of the sphere. You basically put a cube in it with all of its corners coincident with the outer surface, and you project those planes out of the cube. Those become the break lines. And then on the bottom surface, you project these cuts onto those spherical planes, which creates this opening and allows it to open and close. So I was like, okay, I can make a ball that opens in a cool way. So next was to refine it a little bit more and make it completely hollow. So this way the mechanism truly does just lie in that outer surface as much as I could. So now that I had at least the kaleidocycle, I at least had moved from this to this. You can actually see that they're the same mechanism size. So I wanted to start to play with how to install a platform in here. What I was thinking was, if I have hard points of these joints, maybe I can support a platform here. And you see here, these are 120 degree angles. You have 3 of those, 360 degrees. As I open it and close it, those lines are moving down in space, but the angle in that projected plane is still 120 degrees. So I was like, okay, what if I take a little platform and take little tracks for these joints to run in? and I make them curved to accommodate the movement of those joints in space. So I put this little guy in here, and I open it and close it. Look, it moves up and down. And it doesn't go anywhere, and it's flat. So this was just kind of the very, very, very first test of that. Then I was like, okay, how big can I make this? I want to occupy as much space as I can inside the sphere without hitting any walls. You can see it's practically tangent to this edge, and show that I can actually have a fairly large platform inside the sphere, because I also have a much larger payload on the inside. And I didn't want to have to make the sphere comically large. So this showed that I could at least have a deterministic path on a hard platform that could hold a watch. But then, that can happen. It can fall right out. So what I did was I needed to make it so that this track, as it went around this curve, it followed as much of a curve, a straight circle as possible, so that the point of rotation had an equal distance to the mounting location in multiple positions. What that made sure of is that there was no increase or decrease in stored energy, which would cause that thing to flip up and down. And then I could attach it with a piece of elastic. So that's what I tried to do with this prototype. So this is V52 on the 8th of October in 2020. This has been a long journey. So you can see on the inside here, there are pieces of elastic that go down in, and when I open and close it, you can see my joint here, the track, and then you can barely see a little piece of elastic that swings along these slots. And this curve is derived, and this place where it goes down is positioned such that it makes that path be equidistant to the point of rotation as much as possible, so that it doesn't want to whip closed or opened. But there was not a single solution for that was constant length. So this wants to be in some intermediate position. So it goes down, it wants to be there. It even kind of like snaps open. It goes over center a little bit. And it held it pretty well, honestly, but like you could still stretch it. I was worried about things like, how long are these gonna last? How many decades they're gonna last before they get brittle? And it still just seemed like it was cheating. So again, independent of that, there's still the separate projects of the enclosure and the platform. So the thing with 3D printed prototypes is that any degree of compliance in the mechanism can hide any problems in something that's close to being a single degree freedom. So it can let you get away with things that then when you make it hard, it might bind. So in my development, when I get to hard prototypes, which are usually the prototypes that are made with the production intent materials, in this case aluminum, I start calling them Mark 1, Mark 2, Mark 3, etc. It's probably inspired by Iron Man. So from here, I made Mark 1, which was a machined aluminum prototype. And bigger than this. Really, I tried to make it as small as I could because I didn't want something that was, again, comically large. So, and it was immediately apparent that this thing could move in a really, really cool way. What is in here then in the Mark 1 was when I was moving through this development process, the platform here has a fixed vertical position on the joint. It turned out that if I made it so the platform could move up and down a little bit with a fixed length link, I could actually make a truly rigid mounted mechanical carrier on the inside of here. So this is my McMaster Hackathon rod ends with a spherical joint. And it's truly a single degree of freedom platform. That was a really big deal for Mark 1. So, and then I started to learn more about the mechanism itself. So from here, I pivoted over to a larger sphere. So one of the problems was just that this opening was not big enough for a watch, in my opinion. So like it could work, but I really wanted it to sit down in a bit farther. I mean, I'll have another video about how the insert and pillow design worked. I wanted to at least have parity, so even if this would fit, the having parity with at least the amount of clearance that a standard watch would have was an important part to me, so I didn't have to justify it myself. So anyways, Mark II was going to a larger enclosure that could fit a standard pocket size. Again, I'll talk about these details more later. So showed that I had the right enclosure size, showed that I had a nice clicky side of things, but there are some problems that I discovered here. So that contact is between this panel edge and here. So what's happening is if I have any slop or movement here, like 2/1000ths of an inch of slop on this joint will create 40/1000ths of an inch of slop here. So if I want to have a really small break line of 15/1000ths of an inch, I need a very, very tight tolerance control here to resist tapping there. Also, this thing is pretty shaky. The magnets are a little forgiving, but you'll see that on this guy. So it started to reveal that I had coupling between the joint design and some of the sounds and movement of this. Also, you see on this prototype, I have torque striping. I'm just putting a Sharpie mark because what I had happening was these were joints where I just had just a shoulder screw going through and a reamed hole, and then just enough clearance for it to run clearly. But if I was a little off, it would grip the shoulder too much and back out the screw. So I had this kind of competition between joint quality and the likelihood of it just unscrewing itself. So it was then apparent that I needed to start to play with both reducing joint slop and increasing accommodation for joint slop. So I'm gonna skip over Mark 3 and 4 and go on to Mark 5. So in Mark 5, by Mark 5, I had added some features like additional clearance that for even some amount of variation would still prevent contact here. And this is where I started to play around with bearings. So there's a flange bearing here, I think a plain bearing on the inside, and this started to work, but it was so that now I had smooth movement. I could crank these down as hard as I wanted, but now it was too loose and very, very whippy. And then still, even with the bearings and everything, I probably have an extended race or maybe a flange bearing in here, but basically using an extended race bearing. I had too much rocking. You can usually tell it by moving this joint here. So now I've gone the other extreme, added in features to avoid that contact. Mark 6 is one of the place where I finally played around with different combinations and actually got rid of that contact. So the important thing here is that when you open and close it, you only hear contact at the very, very end. You don't hear a click snap. Whereas these, you hear a click snap. Because that little guy is this contacting that. So the critical thing here, and there's no slop in this compared to this guy, which is it's a little shaky. So the way this worked was adding, I have bearings, but also a preloaded bushing on the bottom. The bushing is wide contact area, so that avoids some of the heel toe that's left over by the bearing, but also that bushing interface adds some of the drag so that now it's really pleasantly opening. When I open it, it moves, but it's not like I'm driving that by pressing it on here. So, it went through all these different iterations to get to this point. Even little details like learning that the rod end sweeping around would contact the link, so having spacers, having custom head screws, because as the link goes in, it swings, and if it contacts the carrier cap, it'll actually undo the screw. All these silly little improvements over time. So the thing that I'm probably the most proud of, I'd say like, yeah, maybe the thing that I'm the most proud of is the fact that this kinetic carrier works. So what you end up having is you have this shared link in the middle and a pin joint going across here and a spherical joint. And you can see the links moving on the inside. You can also see them on the back, swinging in. So yeah, this is the Mark 6 prototype. The final challenge for like the last year, honestly, was even after having the mechanism work, even after having the watch platform work, was just getting the finishing right. So you can see here, you can create that spherical surface, but you get a lot of chatter because of what's referred to as a hook feature in machining, and it wants to clap around. So you can take those machined features and then polish them off, but if you polish them too aggressively, you get pillowing. So it makes those edges kind of look rounded in, and honestly, I think it looks more like a soccer ball, though that curvature kind of breaks the illusion of it being a continuous sphere. Also, that polishing process, if the material is too thin, can heat the material so much that it changes its temper, which then that temper variation will show up during anodizing, during the very last step. So it's kind of like if you weld a part. So that was then going to this process, which is more careful polishing, and then an etched finish. So if you do too aggressive a bead blasting, now you'll get your beautiful matte finish, no pillowing, but the matte bead blasting will pick up scratches. So having to go to an etched finish is what avoids that scratching, especially on the final production unit. So yeah, so it's been a long journey to get here, and but yeah, I think what we arrived at mechanically and kinematically is really awesome. We already had a utility patent granted on this external Kaleidocycle. Another bit of IP that we're gonna try to patent is this carrier application. So it's the ability to rigidly suspend something inside a Kaleidocycle without binding it. It's just, yeah, something that was fun and took a lot of hours. So yeah, hopefully this additional insight is interesting to some people. Again, it's something that I'm like pretty proud of and have enjoyed. And it's things that are kind of hard to, I guess ideally, these are details that you don't really even know are there. Because the user just wants to enjoy them in a tactile way. Oh yeah, this is another example of like, when they polish it, they can't do it so much that it's a very sharp edge. So also having to address that in production, it's such a long journey. So anyways, thanks for watching. I hope the people that get to touch this can feel the results. I hope people that watch this can still appreciate it. And yeah, thanks a lot.